Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. This is the 8th module, the heat transfer phenomena of non-Newtonian fluids. In the heat transfer part we have two modules. We have already finished one module. This is the second module on heat transfer phenomena of non-Newtonian fluids. So, the lecture in this module, the title of this lecture is the temperature distribution in fluids confined between two cylinders. So, we have two cylinders. In between these two cylinders an incompressible fluid is confined and one of the cylinder is rotating. So, because of this one how the temperature distribution is varying, because now both the cylinders are at different temperatures from each other. So, non-isothermal conditions are existing. So, from one heated cylinder to the cold cylinder, the heat is being transferred through the fluid. So, in that fluid region how the temperature distribution is varying, that is what we are going to see in this lecture. Remember, in one of the previous modules we have taken a similar problem, the viscous dissipation in coaxial cylinders, where what we have taken two cylinders almost touching to each other, that is the radius of the inner cylinder and outer cylinders are almost close to each other, or the ratio between the inner and outer cylinders is almost approximately close to the 1. So, such cases we have taken where the fluid is confined only in a very narrow region. So, under such conditions what we have taken that the curvature effect can be neglected because the flow region is very narrow, and then even though that geometry is cylindrical, we have solved the problem using the Cartesian coordinate system. But now we take a similar problem, but here what we do here, we take the narrow gap whatever is that we increase. So, the gap between these two cylinders is now sufficiently large, it is not very fine, it is small, still small, but not very small. So, it is still small because we have to incorporate the viscous dissipation effect as well. So, now how the temperature profile changes in these conditions, where the gap is slightly it is in fairly low, but in the moderate range, it is not very small, right. So, under these conditions we take a fluid and then see how the temperature profile changes for this fluid from one cylinder surface to the other cylinder surface. So, this is the inner cylinder whose radius is lambda r, right, and then this is the outer cylinder whose radius is capital R. So, the ratio between these two inner cylinder to the outer cylinder is lambda, and then lambda is not close to 1 like the previous problem, the gap is sufficiently enough. Now, what happens here, the outer cylinder, this outer cylinder is rotating with some angular velocity omega naught, right. So, the inner cylinder is at the temperature T lambda, and then outer cylinder is at temperature T1. So, because these two temperatures are not equals to each other, because of this temperature difference between these two, the heat is being transferred between these two regions, and then that heat is being transferred through this fluid, whatever the fluid, this confined area, whatever this confined area is there, in this area the fluid is filled in, right. Now, the how the heat transfer is changing here. So, let us say this rotation is there, outer one is rotating, inner one is the fixed one. So, what you expect here, how the flow will take place, what you expect here, the flow is to be rotational, right, because it is rotating in a particular direction. So, in that direction you expect the flow to be rotating like this, something like this, right. So, what is this? You need to know this rotational velocity. So, this rotation velocity is theta velocity, only v theta velocity is existing, and then it is changing with respect to r. Why it is changing with respect to r? Because at r is equals to small r is equals to lambda r, it is stationary, that is v theta is 0. At r is equals to small r is equals to capital R, it is rotating with omega naught velocity, angular velocity. So, in the radial direction it is varying, and then further what we understand this we have the laminar flow kind of thing, whatever the flow is taking place in the upper half, the same flow would be taking in the lower half, that is the flow is symmetric in the theta direction. So, these are the schematical representation of the problem. So, the velocity, only v theta velocity is existing, it is function of r, and then temperature is function of r, because at one cylinder surface temperature is T lambda, at the outer cylinder that is temperature is T1. So, because of this temperature gradient, temperature difference, the heat transfer is taking place in the radial direction. So, that is gradient is in the radial direction. So, T is function of r. Pressure is function of r, obviously we understand. It can also be function of z if you take the vertical configuration of the cylinder. If you take the horizontal, then pressure will also be function of r only, right. So, this is the schematic representation of the problem. Now, if you see the statements kind of thing, consider an incompressible liquid confined between two coaxial cylinders. Outer cylinder is rotating at steady angular velocity omega naught, inner is stationary. The ratio between radii is lambda and it is to be fairly small, not very small, fairly small, but not very small, that is it is close to 1. So, it is not that small, it is small, but it is not close to 1. So, that the curvature of fluid streams must be taken into account. So, what does it mean? Now, we have to solve this problem in cylindrical coordinates only. Now, we cannot take that the Cartesian coordinates avoiding the curvature effects kind of things because of this fairly small gap. It is not very thin gap, right. Temperature of inner and outer surface of angular region are maintained at T lambda and T1, and these two are not equals to each other. Assume steady laminar flow and neglect the temperature dependence of the physical properties. Whatever the rho, Cp, mu, K, these physical properties, assume they are independent of the temperature difference, right. That means the temperature difference is in the moderate region, that they are not, that is not going to affect the physical properties rho, Cp, mu, K, etc. So, obtain the temperature distribution in confined liquid region. So, now we have to simplify the energy equation in order to get the temperature profile. But in a energy equation, we have the velocity terms as well, because whatever the heat transfer due to the convection is there, that is because of the bulk flow. So, we should know how the flow is changing, velocity is changing in this confined region, that we should know. So, what we should do? We start with the our conventional method of simplifying the continuity equation, then simplifying the equations of motion, and then we use the we get some kind of information about the velocity and pressure distribution from equation of motion. We solve those equations to get the velocity and pressure distributions, then that velocity profile we will be using in the energy equation. So, let us start with the assumptions before going into the solving this problem. So, what we assume? Assume the Newtonian incompressible fluid. What type of fluid, it is not mentioned in the problem. So, what we take? We take the Newtonian fluid, and then flow is steady and laminar, constant physical properties, that they are not changing with the temperature difference, and there is no reaction. And then we understand from this schematic only V theta is existing and it is function of R. Temperature is also function of R only. Temperature is function of R only. Pressure is function of both R and Z if we take the vertical cylinder. If you take the horizontal cylinder, then this may not be there, right. So, the configuration whether the horizontal or vertical cylinder, it is not mentioned. Let us take the vertical cylinder case thing for us like this, and then take this whatever the pressure variations in the z direction, that also we take into the consideration if required to solve our velocity distribution profile. So, equation of continuity in cylindrical coordinates, we have dou rho by dou t plus 1 by r dou by dou r, rho r v r plus 1 by r dou by dou theta, rho v theta plus dou by dou z, rho v z is equals to 0, right. Here we have the steady state assumption. So, first term is 0, and then there is no V r velocity existing and there is no V z velocity existing, only V theta existing. So, what we get from here, from equation of continuity, dou V theta by dou theta is equals to 0, because from here we understand two things, that V theta is function of R only and then it is not function of theta. What does it mean by the flow is symmetry? Flow is symmetry, that is what we see. So, simplifying of equation of continuity has two advantages. First thing is that whether the flow situation is satisfying the equation of continuity, that is one check. Other check is that we can get some kind of boundary conditions or information about the flow. Sometimes from the problem statement we do not know, we may not know whether the flow is fully developed or not, we do not know whether the flow is symmetrical or not. So, those kind of information we can get from simplifying the continuity equation. So, by from this problem it has not been given whether the flow is fully developed flow or whether the flow is symmetric, etc. So, but now from the continuity equation we understand that the flow is symmetric in the theta direction. Okay. So, equation of motion, now we start simplifying these different equations of motion. We start with the r component. rho dou Vr by dou t plus Vr dou Vr by dou r plus V theta by r dou Vr by dou theta plus Vz dou Vr by dou z minus V theta square by r is equals to minus dou p by dou r plus mu dou by dou r 1 by r dou by dou r Vr plus 1 by r square Vr by dou theta square plus dou square Vr by dou z square minus 2 by r square dou V theta by dou theta plus rho gr. This is what we have, right. This is the r component of equation of motion. Now, we have to apply the constraints of the problem to see how many of these terms can be neglected to get some information about the pressure and then velocity. That is what we are going to see. So, in the LHS, because of the steady state assumption, the first term is 0, Vr is not existing, V theta is existing, but Vr is not existing. So, this term overall this term is 0, Vz is not existing, V theta is existing. So, that we cannot cancel out. So, pressure in general we do not have any information about true boundary conditions, true information about the pressure we do not have. So, this will retain as it is. So, about the velocity Vr is not existing, Vr is not existing, Vr is not existing. So, these terms are cancelled out, 3 terms. V theta is existing, but dou V theta by dou theta is 0 because of the symmetry that we are getting from the equation of continuity. From equation of continuity, this we have seen, and then in the radial direction there is no gravity. So, what we get from here, rho V theta square by r is equals to dou p by dou r, that is whatever the change in pressure in the radial direction is there, that is given by rho V theta square by r. So, we have to find out V theta and then substitute V theta here, then we can find out the pressure distribution in the radial direction. That is not required as of now. So, we will not further simplify it as of now. Now, then is the theta component of equation of motion we start. So, this is given here. So, rho dou V theta by dou t plus Vr dou V theta by dou r plus V theta by r dou V theta by dou theta plus Vz dou V theta by dou z plus Vr V theta divided by r is equals to minus 1 by r dou p by dou theta plus mu into dou by dou r 1 by r dou by dou r V theta plus 1 by r square dou square V theta by dou theta square plus dou square V theta by dou z square plus 2 by r square dou Vr by dou theta plus rho g theta. This is the theta component of equation of motion in cylindrical coordinate system. So, applying the constraints, steady state first term is 0, Vr is not existing, V theta is existing, but V theta is not function of theta direction because of the symmetry of the flow, Vz is not existing. So, Vr is not existing. So, LHS all terms are negligible, they can be cancelled out, right. Dou p by dou theta also we can cancel out because we have seen from the continuity that the flow is symmetry, that is what we found. So, then even though for pressure we do not have any information in general, from the symmetry limitations we can say that dou p by dou theta is also 0. If dou v theta by dou theta is 0, if the flow is symmetric in theta direction, the pressure will also be symmetric under these laminar conditions. So, dou p by dou theta is also 0. So, next V theta is existing and it is function of r. So, this term we cannot cancel out. Okay. Then V theta is existing, but it is not function of theta. So, this term is cancelled out. V theta is existing, but it is not function of z. So, this term is also cancelled out. Vr is not existing, this term is not there, and then there is no gravity in the angular direction. So, what we have? We have dou by dou r 1 by r dou by dou r of r V theta is equals to 0. This equation we can make use in order to get the velocity profile V theta as function of r. Next is the z component of momentum equation. So, it is given here. What we have, rho into dou Vz by dou t plus Vr dou Vz by dou r plus V theta by r dou Vz by dou theta plus Vz dou Vz by dou z is equals to minus dou p by dou z plus mu into 1 by r dou by dou r dou Vz by dou r plus 1 by r square dou square Vz by dou theta square plus dou square Vz by dou z square plus rho gz. This is the equation that we have. So, now here also we apply the constraints assumptions of the problem to simplify further if we get any additional information. So, then steady state first term is 0, Vr is not existing, V theta is existing, but Vz is not existing, Vz is not existing. So, left hand side all terms are cancelled out. Pressure we do not know how it is varying with the z direction. So, let it be as it is. Vz is not existing, so this term is 0, Vz is not existing, so this term is also 0, Vz is not existing, so this term is also 0. So, if you take the vertical cylinder, then the gravity would be in the z direction. So, then let us keep it as it is, and then Gz is equals to minus G if you take the flow downward kind of thing. So, then we have the pressure as function of Z also, that is in the z direction the pressure is the hydrostatic pressure of the fluid only. The pressure is the hydrostatic pressure only in the z direction, whereas in the radial direction it is function of velocity as given by this equation number 2. Now, what we do, we take this equation number 3 and do the integration and obtain the integration constants applying the boundary condition in order to get the final velocity profile as function of r. So, that if you do, we have this equation, right. So, from equation number 3, d by dr of 1 by r d by dr r v theta is equals to 0. So, when you integrate, so 1 by r d by dr r v theta is equals to C1. Let us take r to the other side. So, d by dr of r v theta is equals to C1 r. If you integrate again, r v theta is equals to C1 r square by 2 plus C2. Now, take the r to the left hand side, we have v theta is equals to C1 r by 2 plus C2 by r. This is what we have. Now, we have two boundary conditions for the velocity profile, and then there are two unknown constants. So, applying these two boundary conditions, we can know these constants. When you substitute these constants in equation number 5, you will get the velocity profile you will get. What are the two boundary conditions? That is, the inner cylinder is stationary. So, at small r is equals to lambda r, v theta is equals to 0. So, in this equation number 5, substitute lambda r in place of r and then equate v theta to 0. So, 0 is equals to C1 lambda r by 2 plus C2 by lambda r. The other boundary condition is that the outer cylinder is rotating with omega naught angular velocity. So, if the angular velocity is omega naught, if you convert into the linear this thing, then it has to be multiplied by r. So, at r is equals to capital R, v theta is equals to r omega naught. So, r omega naught is equals to C1 r by 2 plus C2 by r. Now, this equation what you do? You multiply by lambda either side. So, that lambda r omega naught is equals to C1 lambda r by 2 plus lambda C2 by r. So, this equation number 6a, this equation number 6b. Now, what you do? You do 6a minus 6b. So, that this C1 lambda r by 2 terms would be cancelled out, and then C2 you can obtain. You can obtain the C2. When you do that, you get this thing minus r lambda omega naught is equals to C2 by lambda r minus C2 lambda by r. So, from the right hand side, let us take C2 common, then what you have? C2 1 minus lambda square divided by lambda r. So, C2 is equals to minus omega naught r square lambda square by 1 minus lambda square r. The same thing you can write as omega naught r square lambda square divided by lambda square minus 1. This is C2, equation number 7a. Now, what you do in equation number 6a, this equation, that is 0 is equals to C1 lambda r by 2 plus C2 by lambda r. This is the equation number 6a. In this equation here, what you do? You substitute C2 is equals to omega naught lambda square r square divided by lambda square minus 1. This is what substituted, and then you simplify. So, you get, you take this term other side, C1 lambda r by 2 is equals to omega naught lambda r by 1 minus lambda square. So, C1 is equals to 2 omega naught divided by 1 minus lambda square. So, now both C1 and C2 are known. So, this C1 and C2 if you substitute in this velocity profile, that v theta, what we have? V theta is equals to C1 r by 2 plus C2 by r. This is C1 r by 2 plus C2 by r. This is what? V theta. Now, here this is C1 is nothing but 2 omega naught by 1 minus lambda square. C2 is nothing but omega naught r square lambda square by lambda square minus 1. If you substitute these two and then simplify, you get this equation for the velocity profile. Now, what you do? From this equation, you rearrange that so that you have the r omega naught as a common term, and then remaining thing is the multiplied fraction. What is the fraction? So, that it can be contributed, it can be analyzed as, the maximum velocity, angular velocity is r omega naught. So, how it is decreasing? if the r is decreasing from r is equals to capital R to r is equals to lambda r, how this v theta is decreasing, that you can get from this profile easily by calculating this fraction. So, this is the velocity profile. So, whatever the confined fluid is the rotating in the theta direction. So, that theta direction velocity is given like this. So, now in the RHS of this equation everything is known. So, if you want to know the v theta velocity at any location between r is equals to lambda r to r is equals to capital R, you can calculate using this expression. Now, in energy equation we will be solving this term is required, r d by dr v theta by r. So, then let us do the same thing. So, now what we do from this equation, what you do, you take from the numerator you take r common and then bring that r to the left hand side. So, then you have v theta by r is equals to this thing, or the simply rearrangement of this v theta expression by taking small r to the left hand side, we have v theta by r is equals to omega naught minus omega naught r square lambda square by r square whole divided by 1 minus lambda square. Now, differentiate this v theta by r with respect to r. So, then we have this particular term, that is d by dr omega naught 1 minus lambda square minus d by dr omega naught 1 minus lambda square r square lambda square by r square, right. So, this is a constant, it is not changing with r. So, then it is 0 minus here in this term r square lambda square omega naught by 1 minus lambda square is constant, that is as it is. Differentiation of 1 by r square is nothing but minus 2 by r cube. So, we have d by dr of v theta by r is equals to 2 omega naught divided by 1 minus lambda square r square lambda square by r cube. Now, if you take one r to the left hand side, we have r d by dr v theta by r is equals to 2 omega naught r square lambda square divided by 1 minus lambda square small r square. So, this we may be using in simplified energy equation. So, that we are going to do now. We are doing in advance because I know this is required for solving the energy equation. This term appears in the viscous dissipation term. So, now the energy equation, if you take energy equation here is given here in the cylindrical coordinates. In the cylindrical coordinates, energy equation is rho Cp tilde dou T by dou T plus Vr dou T by dou R plus V theta by R dou T by dou theta plus Vz dou T by dou Z is equals to K 1 by R dou by dou R dou T by dou R plus 1 by R square dou T by dou theta plus dou square T by dou Z square plus mu pi V. So, left hand side the temporal term, this is temporal term, and then remaining 3 terms are the convection terms. Right hand side these first 3 terms are the conduction terms, and then last term is the viscous dissipation term. So, here we apply the constraints of the problems in order to simplify this equation, so that we can get the temperature profile. So, it is a steady state problem. So, first term in the left hand side is 0, Vr is not existing, V theta is existing, but the flow is symmetry. So, dou T by dou theta will also be 0 because of the symmetry boundary condition. If the flow is symmetry in the theta direction, the corresponding temperature profile in that fluid region will also be symmetric in the theta direction. So, dou T by dou theta is also 0, Vz is not existing. So, LHS all terms are negligible. So, discarded. Right hand side term, temperature is function of R. So, we cannot cancel out this term. Temperature is not function of theta because of the symmetry, and then temperature not function of Z. Because of symmetry, dou T by dou theta is 0, and then temperature is not function of Z. So, dou square T by dou Z square is 0. This viscous dissipation term, there are several terms as we have already done for the Cartesian coordinate system. So, I just leave it to the students, pick up any standard transport phenomena book and then see what is the viscous dissipation term for cylindrical coordinates Newtonian fluid, and then apply the constraints of this problem. Then you will understand that pi v is nothing but only this v theta by r terms only, v theta terms will only as function of r, those terms only will be retained. So, you have mu into r dou by dou r v theta by r whole square, only this term is existing. This is after simplifying, this term is after simplifying whatever viscous dissipation terms are there, only one term is will be there, that term is this one. This you can try because for the Cartesian coordinates we have already done. So, I am not doing it again, I am leaving it to you as a exercise. So, what we have after simplifying this energy equation, 0 is equals to k by r dou by dou r dou t by dou r plus mu r dou by dou r v theta by r whole square. So, we have just in the previous slide we have derived what is this r dou by dou r v theta by r in advance. So, that we substitute here, we substitute, that is nothing but r dou by dou r v theta by r is nothing but 2 omega naught r square lambda square 1 minus lambda square small r square. This is nothing but r dou by dou r v theta by r, and then whole square is required, so then whole square. So, if you take this k terms to the left hand side, you have the same equation like this, minus k by r dou by dou r dou t by dou r is equals to 4 mu omega naught square r power 4 lambda power 4 divided by 1 minus lambda square whole square 1 by r power 4 small r power 4. So, this small r power 4 I have written separately because we are going to integrate this equation with respect to r only, rest other terms are all are constants. So, now before integrating what we do, we can non-dimensionalize this equation so that we can do integration easily simply. So, what we take small r by capital R is nothing but xi, that is what the scaling parameter we take. Scaling parameter xi is equals to small r by capital R, and then scaling parameter capital theta is nothing but t minus t lambda by t1 minus t lambda. So, when we apply these scaling parameters in this equation, we have minus k as it is, small r is nothing but from the scaling parameter capital R xi, d by dr is nothing but r d xi multiplied by r is nothing but r xi, and dt is nothing but d theta d capital theta multiplied by t1 minus t lambda. So, that is what here from here. So, from here what we get, dr is nothing but r d xi, and d capital T is equals to t1 minus t lambda d capital theta. So, that is what is substituted. So, dr is nothing but capital R d xi is equals to right hand side, this particular time is constant. So, let us not touch them, r power 4 is capital R power 4 xi power 4. So, now here what happens, this r cancelled out, okay, and then similar terms if you cancel out, that is the only term that you can cancel out here. So, what you do here, you can cancel out r power 4 and then r power 4, right. So, what you do now here, this minus k divided by r square that you take to the other side. So, what you have, r square divided by k, minus k by r square, when you take it to the right hand side, it becomes r square by k. So, here what are the terms remaining in the left hand side, 1 by xi d by d xi, 1 by xi d by d xi, inside xi is as it is, and then you take t1 minus lambda to the right hand side. So, then t1 minus lambda t1 minus t lambda is other side, t1 minus t lambda you take to the right hand side. So, it comes out to be t1 minus t lambda as a here divided by this one, right. Then d capital theta is as it is divided by d xi. So, left hand side what we have, 1 by xi d by d xi of xi d theta by d xi is equals to minus 4 mu omega naught square r square lambda power 4 divided by k 1 minus lambda square whole square t1 minus t lambda 1 by xi power 4. So, this is here, these things you can take as some constant n which is similar to the Brinkmann number that we have seen for one of the previous problem for the viscous dissipation case, right. So, here also viscous dissipation is there because of this additional term is there, that constant is similar to the Brinkmann number. It is not the Brink number exactly, but it is similar to that one. So, then this xi and xi power 4, if you take out xi cube you will have. So, then what you have, 1 by xi, in the next slide we see that 1 by. So, this equation 1 by xi d by d xi of xi d theta by d xi is equals to minus 4 n by xi power 4. So, now here this xi and then this xi power 4 we cancel out. So, xi cube you have. So, this equation become d by d xi of xi d theta by d xi is equals to minus 4 n by xi cube. So, now this equation if you integrate, you have here minus 4 n xi power minus 3 plus 1 divided by minus 3 plus 1 plus integration constant C1 or xi d this you can simplify xi d theta by d xi as it is equals to 2n by xi square plus C1. Now, you take this xi to the right hand side. So, you have 2n by xi cube plus C1 by xi. Now, again if you integrate, you have theta is equals to 2n xi power minus 3 plus 1 by minus 3 plus 1 plus C1 ln xi plus C2. So, theta is equals to minus n by xi square plus C1 ln xi plus C2. So, if you apply the boundary condition here, so then you will get the C1 C2 constants. So, then finally temperature profile would be available. So, we have two boundary condition at r is equals to lambda r, we have T is equals to T lambda. So, that means if you convert it in terms of xi, so at xi is equals to lambda, theta is equals to 0, because theta is nothing but T minus T lambda by T1 minus T lambda, right. So, if T is equals to T lambda, then theta should be theta T lambda minus T lambda by T1 minus T lambda, that is 0. This is one boundary condition. So, when you apply this one, at xi is equals to lambda, theta is equals to 0. So, theta is equals to 0 is equals to minus n by lambda square plus C1 ln lambda plus C2. Other boundary condition, that is at r is equals to capital R, that is outer cylinder, T is equals to T1. So, that means xi is equals to 1, r is equals to capital R in the sense xi is equals to 1. So, then theta is equals to T minus T lambda by T1 minus T lambda, that should be 1, because now T is equals to nothing but T1. So, at xi is equals to 1, theta is equals to 1. So, that is equals to minus 1 by 1 square plus C1 ln 1 plus C2. So, this is not possible. From here what we get, C2 is equals to n plus 1. Now, this C2 if you substitute here, you can get C1. So, from here C1 ln lambda is equals to n by lambda square minus C2. So, n by lambda square, C2 is equals to n plus 1. So, minus n minus 1. So, C1 is equals to n by lambda square ln lambda minus n by ln lambda minus 1 by ln lambda. This is what your C2. So, C1, C2 are available. Now, this C1, C2 you can substitute in this equation to get the dimensionless temperature distribution. So, when you do that one, this is your theta. So, C1 is this one, C2 is this one, you just obtain it. So, minus n by xi square is as it is. C1 multiplied by ln xi, C1 is ln n by lambda square ln lambda minus n by ln lambda minus 1 by ln lambda. So, this all multiplied by ln xi plus C2 is nothing but n plus 1. So, what you do here, you separate the terms having n and then without n. So, without n we have only these two terms, 1 minus ln xi divided by ln lambda. This is the only term without n. So, remaining terms n is there in remaining 4 terms. What we do in the remaining 4 terms, we take the terms which are having ln xi by ln lambda common. So, then we have n into 1 minus 1 by xi square minus 1 minus 1 by lambda square ln xi by ln lambda. This is what we have. This is the temperature distribution in the dimensionless form, non-dimensional, that scale parameters theta and then xi we have used. So, now we replace theta is equals to T minus T lambda divided by T1 minus T lambda, that is the theta, and then xi is nothing but small r by capital R, that substitute here, and n is nothing but this parameter mu omega naught square r square lambda power 4 by k 1 minus lambda square whole square T1 minus T lambda is that n. So, when we substitute all these things, you have this temperature distribution. So, this is the temperature distribution of confined fluid, that is confined between two coaxial cylinders having fairly small gap but not very narrow gap. So, this problem is taken from the reference book Transport Phenomena by Bird, Stewart and Lightfoot. Thank you.